All right. Okay. Okay, Zoom. We're having troubles with the camera. So it's not recognizing. Yeah. Camera. Yeah, still not seeing it. Ah, there it is. Okay.
Where do you play ball? High school. Just on Mondays, I go with some friends to Rhodes Middle School. It's like central San Antonio.
Have to get out there.
For real?
Oh yeah, it's ball. That's ball.
All right, online in Zoom, or you're still seeing a black screen from me, right?
Yes, sir.
So then the problem becomes having to use this camera again, which is a piss poor substitute. camera again. See if it'll work better than that one. Oh, come on, come on. Oh, yeah. Try again.
My son said, "And then you went to the toilet."
Oh,
So that's now.
Tom was a stubborn one. Get him to. That was first frozen. Okay. Really doesn't want to see the camera. And USB camera. And we got camera.
I'll show up. Okay.
And then roots.
Yeah.
I'll let you know when-
Where did you get your bracelet from?
It's a Navajo.
What part?
Yeah, I'm a huge fan of anything Native American as far as art and jewelry. I used to wear 4 or 5 turquoise and silver rings. I have another bracelet I used to wear, but it got damaged. So I put R in it and okay, hopefully things will show up and you can see it. If it can't, then I don't know what to do. Stupid machine. Okay. Trying to remember where we ended up. The sinusoidal, the function, the graphs.
I was thinking about asking you if you would help organize the chapter.
Yeah, I mean, anything that I found really useful, they want to copy, just, you know, I'm always gonna keep it up here, so.
Okay.
Whatever.
Those of you on Zoom, is the screen showing up okay?
Of course.
It's probably not all that wonderful.
We can see the screen.
is being reflected right here. So I just need to be aware of that, not right there.
Some people organize like that. I just go by like a day kind of. And like, let's say, it's really like, so if you take off like this, and this would be 22. 21. And this number is just, going by day. You just got here.
Okay.
Yeah, I mean, honestly, I feel like if you want something, I want to say this stuff.
I don't even bring notes, bro. I don't bring anything.
Yeah, but you were always on top of this stuff, I'm really.
But I don't even have, I don't have anything. I have to come to class every time looking for a pencil and paper.
I don't feel like I'm.
Okay, I'm gonna go ahead and get started. I'm gonna back up, and we had done this.
Yes.
Okay, and so, yeah. And come on, I just. What is wrong with the machine again? No, wrong button. No, it's not letting me advance. Oh, yes, it is. Okay. So, the sine and cosine functions, talking about the graphs. And so, the graph, we're going to graph the sine y equals the sine of x. So we're no longer going to be using theta, but when we start graphing, we're going to be using x and y. And again, this is going to be f of x equals sine of x. And also going to be talking about what this form of the equation looks like, what it means. So we have y equals a times the sine of omega x. Yeah, this funny looking W is a Greek letter omega. And it has significance in mathematics and in electronics as well. So we're talking about, and we'll talk about the cosine and determine amplitude and period of sinusoidal functions. And these two cosine and sine are sinusoidal. It comes from the same sine function, and it talks about sinusoidal functions. So it keeps going up and down, up and down, up and down. So we have an amplitude that's talking about how high it goes, how low it goes, and the period talks about over what numbers of x do the y values repeat. So here is one iteration. Here's a copy of that iteration. Here's another copy. So these iterations, this is the period. So I start at this value and up and down, and then here I am again, starting over. So that's what we mean by period. Amplitude is about how high and how low it goes. And omega has something to do with the period. And then graphing, we can use the key functions, we can use the key points of the initial functions of sine of x and cosine of x, and use those to transform, to do transformations to get to whatever this thing looks like. And then find an equation for a sinusoidal graph. So you have a graph. What's the equation look like? It'll either be sine or cosine. Now, we want to graph trigonometric functions in the xy plane. So we use the traditional symbol x for the independent variable or the argument. So theta, the angle, we're calling it x now. So this is different. This is different than the unit circle, and where we talk about angles going around this way, okay? Or the other way. Now we're talking about the x-axis is the angle measure, and the y-axis is the sine or the cosine, depending upon whether you're dealing with sine of x or cosine of x. Here, each point is cosine x, is cosine and sine of the same angle to get your x and y values. Well, we're looking at it differently.
Sorry, can you repeat that one time? We said x is the angle measure and y is the cosine of the sine?
Well, y tells us how far up or down we're going.
Yes.
This point here, we would have a certain x value that gave us this sine value or this cosine value. So the y-axis is either the sine is doing the function on that angle. So if it's a straight sine function, and I'm doing the sine of 30, then y is what? 1/2. So this point here would be 30/1/2, or pi over 6 1/2. Because when we start graphing them this way, we almost always use radians. And so here are the 6 trig functions when we're dealing with them as graphing functions. So now, these two graphs, sine and cosine, look alike, which means cosecant and secant will look alike, but they don't look like they're reciprocal functions. Cotangent, tangent, and cotangent will look alike, and they look way different than anything else. With tangent and the reciprocal functions, we will have asymptotes. Remember asymptotes from college algebra, those are vertical lines that the graph does not cross. So as x approaches that value, it either goes to infinity, either going up or going down, or it comes up from infinity or comes down from infinity. It all depends on what the function is doing. But if it goes up to infinity on this side, it's going to be coming up from negative infinity on this side, and vice versa. So with the trig functions, they won't be on the same. They won't be. They both won't be going up or coming down from positive, or going down to negative, or coming up from negative on the same. It's always opposite. So if it's going down here, it's going to still be going down, but it's going to be coming down from positive infinity. And if it's going up to positive infinity on the other side, it's going to be coming up from negative. Okay. And this is, this is one period of the sine function. Remember we talked about the sine, how the sine starts repeating its y values after you go to 2 pi. The sine of the angles, it's just repeating this cycle all over again. So it's just like I can pick this whole thing up and bring it over here and continue on. So they restricted the domain here for this picture. And on the last thing they talked about on the first slide for this section, the key points. Well, the key points here are where it crosses the x-axis, in other words, when it's 0, and where it equals 1. Because we're going to use those key values to help us graph it, to help us to do transformations. Sometimes we're going to do a horizontal compression or a horizontal stretch. And sometimes we're going to do a vertical stretch or a vertical compression. So it just all depends on where do these points end up. And when you graph these things on a test, I need you to go up. Everybody see? Are you still like teaching out of this room? Yeah. All right. So on the unit circle, we're just looking at if we just look at the sine values, okay, at pi over 6, the sine value was 1/2. So that's pi over 6 gives us 1/2. And at 2 pi, the sine value was 1, because that's this point up over here. And the sine, the y value there was 1. Okay. At 5/6 pi, well, pi over 6 was here, 1/6 pi is over here. And so that's going to be, again, that's going to be 1/2. Right? And then pi, the y value at pi is 0. The y value of 3/4 pi is -1. That's down here, and I skipped this one over here. At 6/7 pi, the y value is -1/2, and at 11/6 pi, it's -1/2 over here, and then back to 2 pi, we're back to 0 again. So we've gone full circle. So this shows the full circle in the y values, which is the sine. That making sense?
Yeah, I just listed the points of the whole circle. Because you know
So
it goes up
if
and then it
if
goes
we
down.
went all the way around, so this point here would be the square root of 2, the square root of 2 over 2, and the square root of 2 over 2. So the sine of this angle would be the square root of 2 over 2, which is about what's that? Halfway between these. So that's going to be about, so that's going to be there. And then 1/3 is about here, pi over 3. This was pi over 4, pi over 3. That's this point here, and that's going to be the square root of 3 over 2. So that's the y value, square root of 3 over 2. And then on the other side, we get to 2 pi over 3, sorry. And so this point up here is going to be the same as this value here. So these values are going to be repeated again just in the reverse order. So pi over 4. So this is 3 pi over 4. So this y value is what's that? Oh, square root of 2 over 2. And so it continues on. So it's just repeating these values, the y values of the unit circle again and again and again. So if you look at the chart of that unit circle, that had 2 pages to it. The second page was the chart where you had all the sign down the left hand back, and you had the ordered pairs all the way down on the right hand side. Well, the y values, that's the y values here from -1 to 1. And then the angles are just going along here. And that was the very first 2 columns was the angle measure. One was in degrees, the other was in radians.
Okay, Bob, what you're saying right now is what's right there, right? You said the y is right here.
Yeah, all up and down here are the y values for this graph. They're the sine of these angle values, which is the y values on this unit circle. With cosine is the same thing. All right, so here they're talking about the properties of the sine function. All right, the domain is all real numbers, and the range goes from -1 to 1. Well, that's real easy to see here. Sine goes from -1 to +1. It's an odd function. We already discussed that. And the symmetry of the graph is symmetric with respect to the origin. It has a period of 2 pi. Kind of discussed. So it goes through all the values from -1 to +1 at least once. For that whole period. Now, I haven't gone through and fixed this. Some of this stuff here is incorrect. Well, I blame the author since he's responsible. But okay, so the x-intercepts 0, pi, 2 pi, 3 pi, 4 pi, 6 pi, and then -pi, and -2 pi, and -2 pi. Okay, so it's all multiples, integer multiples of pi. Yeah, so that's correct. I don't remember which one they got wrong.
In the order that you see on the line.
Well, and that's chronological order. And the maximum value where it's 1 are multiples of pi over 2. Well, it's the even unknown. Odd multiples, but it's not. There's a pattern to how those develop. Those are the right ones. Because it's here at 90 degrees or pi over 2, as long as the terminal side of the angle ends up here, the y value is 1. And so that's what we're talking about. So that's pi over 2 going around once and then coming to it. That's 5 pi over 2 and then 9 pi over 2. So it's pi over 2 plus 2 pi k, where k is an integer. That equals where sine is 1, where it reaches its maximum value. That's all these numbers here. No, k is an integer. A lot of times in these formulas, when you see k, it means an integer. And well, it is an integer, and sometimes there will be stipulations on what kind of integer. Sometimes it's an odd integer, even integer, or just an integer. In this case, it's any integer. Positive.
Sir, on the left side of the screen, it got pretty blurry. Like it's almost unreadable now.
Over here,
Yes, sir.
is it better now?
No, it got worse like in the past 5 minutes. The right side's fine.
Yeah, this is a great little camera for up close work, or as a webcam, not as a document cam or presentation camera. That help a little bit?
Yeah, it's better.
Yeah. Next time I'll bring my presentation. They're supposed to make sure this works right. Yeah, I'm having problems with IT, but. Anyway, and so the minimum value, well, that's when that's 3/2 pi. Or coming this way is negative pi over 2. So it's going to be a similar formula, but I either start at negative pi over 2 plus the 2 pi k, where k is any integer. Or we can say 3 pi, 3/2 pi plus 2k. I mean 2 pi k.
This is for the minimum.
Yeah, for the minimum. Because any multiple of 2 pi added to negative pi over 2 or 3 pi over 2 is still going to have you wind up here. And so the y value there is going to be 1. So those will always give you the minimum value of 1 for sine of x. So we're strictly dealing with this right now. Right. Because with a sine of omega x, that's assuming a is not 1 and omega isn't 1. Then with a, our maximum and minimum value change. So if a is 3, then our maximum value and minimum value go to 3 and negative 3. And if omega is something other than 1, then our period changes. So our period gets compressed towards the y-axis or pulled away from the y.
And we're gonna see some problems like that in the future.
Oh, yeah.
Okay, but as for right now, since we're just introducing this, we'll be able to
right now.
Well, about 2 or 3 slides from now, you'll see it.
Okay.
Next group of slides will deal with cosine. Oh, wait a second. Using transformations, we're going to graph y equals 3 sine of x. Well, here I have sine, which is so I 2 pi 3 pi I over 2 3 pi over 2 5 pi over 2. Here we have -1 to +1. So when the angle is 0, y is 0. When pi is 1/2, well, they were doing 3/4 pi. I mean, pi over 6. So they were doing the 6 pi. Well, I'm just going to go to pi. At pi, it's 1. And at 2 pi, it's back to 0. And at -1. Is that right? No, where did I screw up? Oh, at pi, it's back to 0. At pi over 2, it's at 1. And at pi, it's at 0. And at 3 pi, 3 has pi, it's at -1. And at 2 pi, it's at 0 again. So that means at 5 pi over 2, it's going to be back up to 1. And this is going to go back to 0. And so I can sketch that graph. How accurate is my graph? Yeah, well. Do I care how accurate it is? No, because I just wanted the general shape of the thing. Okay. So this is f of x. F of x equals sine of x. Well, I'm going to call this g of x. Just to give it a different name because I'm dealing with 2 different sine functions. And so what do I do to f to make it look like this? What do I do to it? What do I do to this to make it look like this? Multiply by 3. So I'm multiplying f by 3. So this means I'm multiplying each y value by 3. Remember doing those kinds of transformations? Algebra. So 2, 3. So 3 times 0, 0. So that's not going to change. But 3 times 1 is 3. And 3 times 0 is still 0. And then 3 times -1 comes down here to -3. So that comes down to here. And this comes back to 2. Back to 0, because 0 times 0 is still 0. And they're going to multiply 1 by 3. So that's going to bring it back up to here. And it's going to be at 0 again. So I'm going to use a different color. Because I can. I'm a good friend of Arlingdale School District. And he has about 5 or 10 different colored markers that he uses for it. I just use 2 or 3 different colors. So this is going to be very simple. Whoa. No, a little bit off there. I kind of wobbled.
This is 3 sine x.
Sine x.
3 sine x. This is g of x equals 3 sine x.
So this is y equals 3 sine x. Because we changed the y value. Sine is the y value and we multiplied it by 2. If I multiply x by something, I'm changing my x value. So that'll either bring it towards the y-axis or pull it away from the y. Now, if I came back into the negatives, right, I can go here to negative pi and then negative pi over 2. At negative pi over 2, it's at negative 1, and then at negative pi, it's back to 0. So this would go like that. So this point would come down to negative 3, and you would still be up there, so it comes back down. So that amplitude change, A made it change how high and how low it goes. Okay.
Yep, I see that.
If that was 1/3, then instead of going up 3 times, I'd come down only to 1/3. So at 1/2, it goes up to 1/3. And at 3 halves, it would come down to a negative 1. So it would push it down towards the x-axis. Right. Oh. Huh? Yeah, I gotta erase all my work.
Not like this with visuals. About to see how.
It's the only way I learn this stuff is through the visuals. Professor can talk all day with his words, but unless he shows me it, I'm lost. So especially this kind of stuff. Now, my argument here with their 2 pictures is that the scale factor left to right is different, as well as the scale factor up and down. So it's kind of hard to see truly what happened here. Other than I can go and make this picture fit, but it's going to distort the numbers. So. And the domain here is the same as the domain of the 3 sine of x, because the x values is all the same x values. What changed was the y values. Now, instead of the range being from -1 to 1 inclusive, it's now from -3 to 3 inclusive. So you can either write it as in set builder notation or interval notation. I have a tendency to favor the set builder notation, mainly because that's the way I was taught. But either way is valid. Okay. Now we have -2 sine, 2 theta. Yeah, they definitely switched it up. Yeah, they do it. They're going to do it the same way I would do it. So erase it. Now I have to do it all. So here I have -pi, 0, pi, 2 pi, and I like to go out to 3 pi. Then we have negative pi over 2, and then pi over 2, and then 3 pi over 2, and 5 pi. Assume that this is all of them are 1. That's right. And so at the whole pi is at 0, all the way up, all the way down. So at the whole pi values is 0, and at the high pi values it's either -1, or positive. So this is at -1, +1, -1, so it's at +1. And so now I can sketch the graph a little bit. Down like this. Oops. The wrong spot. Try to erase.
So on the 1 line here, are we dividing by 2 or by 1?
What do you mean?
You get the 1. Zeros and here are the negative number, we put the -2 by. Am I dividing? What am I dividing it by over here? I'm not sure what's that.
Oh, I'm just going in the negative direction now.
But on the Y.
Oh, on the y? Well, at negative pi over 2, it's at -1. And then
So we can substitute that X number. With the negative pi over 2 with an X. To solve that equation. Or am I wrong?
Yeah, sine of negative pi over 2 equals a -1. So
And
this
how
is
did you get the Y? That's the bit I'm struggling with. How do we get the
the
Y?
sine of this, of the x values. These are the x values. These are all the x values. So sine of negative pi is 0. And so that's what this point is, negative pi is 0. Sine of negative pi over 2 is -1, so that's what this point is, negative pi over 2 is -1.
Okay.
So if you come back to the unit circle, going in the negative direction is just like going this way in the unit circle.
Okay.
So these values down here start repeating these values up here, but this is the negative of the, they're negatives of each other in the lines. And since it's an odd function, this point has a mirror image, which is negating both the x and the y. So this is pi over 2, 1. So this will be negative pi over 2, -1. This is 0. 1 pi 0, or 0, yeah, 1 pi 0, and so negative pi 0. Okay, find out both of them. So that's what happens on down the line. So like that point, so wrong. So and that's a repeating nature of sine and cosine. So what I just graphed is f of x equals sine of x. But here, we multiply by -2. So I have a -2 times f of x, which is -2 times sine of x. So I'm just going to multiply the y values by -2. So I'm going to multiply -1 by -2 gives me +2. So this one. This point here bounces up to here. Because now I'm multiplying the y values by 2. 0 times -2 is still 0. -2 times 0 is still 0. But the y value here is 1, and 1 times -2 is a -2. So it comes down here to -2. And so 0 stayed at 0, and now -1 multiplied by -2 comes up to +2. And 0 stayed at 0. And then 1 times a -2 brings it back down here. And then 0 stayed at 0. So now my graph goes this way. What I did was, because I'm multiplying by a negative number, not only did I do a stretch, but I did a reflection across the x-axis. And actually, yeah. Well, the textbook would have done by 2 and then flipped it. So they would do it in 2 steps. I just did it in 1 step. Well, now just flip it. Flip it across the x-axis. Because what the textbook would do is the textbook would bring it down to here like this. By multiplying by 2, and then bringing the negative in would flip it across the y-axis. I just did them both at the same time.
Well, we still haven't done the 2x.
No. So now I'm changing this in here. Okay. Where it gets a little tricky. So when you're multiplying x by a number, so you're changing your argument. That means you're gonna take the x value of the points here and divide them by whatever you're multiplying there. So it's like taking the x values and dividing them by 2. So 1/2 comes to pi over 4. Let me do this.
We divide the argument by 2. Right?
Well, the x, not the argument, the x.
So we're changing the argument.
Right. So 1/2 got moved down to 1/4. So this point got moved over to here. pi, half of pi got moved down to here, so this point got moved over to here. Three halves pi. Well, that's just, dividing by 2 is the same as multiplying by 1/2. And so multiplying 3 halves pi by 1/2 gives me 3/4 pi. So 3/4 pi is here. And so this point, this x gets moved down to here, so this point gets moved over to here. Half of 2 pi is pi, so this point got moved over to here. Five pi over 2 becomes 5 pi over 4. 5 pi over 4 is here, so this point, this x value got moved down to here, so this point got moved over to here. And then 3 pi divided by 2 is 3 halves pi, so this point got moved over to here. Now, I'm not shifting the graph to the left, I'm compressing the graph towards the y-axis. So on the other side, I'm going to be doing something similar. I'm going to multiply by 1/2, that gives me a negative 1/4 pi. So that's this point here. Negative pi over 4. So this y value got moved to the right. So this point got moved to the right here. Half of negative pi is negative 2 pi. So this point got moved over to here. And so now this is our graph. Just missing. That was it. Is there a yellow? I mean,
It's getting scary real fast, Mr. Reed.
oh, this crap.
Not gonna let us drown, right, sir?
Huh?
Not gonna let us drown. Okay, okay.
I'll dive in there with you. Try and help you out of there. Okay. So we had a vertical stretch and a reflection across the x-axis. And then we have a horizontal compression. I don't know if you remember from college algebra. If you're changing your argument by multiplying it by a number greater than 1, then that's a compression. It's different. It's almost like you're doing the opposite of what it would be in the vertical. Because in the vertical, if we're multiplying by a number greater than 1, then it's a stretch. But if you're doing it to the x, it's a compression. So if this was 1/2 x, then it would be multiplying each of the x values by 2 and moving those points out appropriately. So you're thinning it out. The highs and lows don't change. Notice the highs and lows don't change here when you do a compression or a horizontal. Your period changed, our period changed here. The period now is just pi. Okay. Where is mine? So I'm going to run through theirs.
So, our equation, -2 sine times 2x was a compression and
It was a vertical stretch,
a vertical stretch.
a reflection across the x-axis, and a horizontal compression. Oh, they did the flip first. They did the reflection first. So they dealt with the -1. When you multiply by a negative, you're flipping it across the x-axis. And then they're going to do the stretch times 2. So we changed our minimum value. We changed our minimum value to -2, and our maximum value to +2. And then there it is. I very often answer it, and you just don't. And my wife is horrified that I do. Okay. Now. And then they did the big compression. So -pi here went to -1/2 pi. -1/2 pi went to -1/4 pi. 0 stayed at 0. Because a half of 0 is still 0. And then 1/2 pi went to 1/4 pi. And pi came to 1/2 pi. And 3/4 pi came to 3/4 pi. And then 2 pi would come back down to pi. They didn't go as far up as I did. So the amplitude, or what we're multiplying by, makes us determine what our minimum value and maximum value for the function is going to be. And so that's what the domain doesn't change. The domain here isn't ever going to change simply by doing some kind of transformation of the sine function.
Always had your ear pierced. You always had your ear pierced. I'm like just noticing. Sorry, just noticing. You never wear that there in there?
It's been there.
Yeah, it's been there, man.
I never take it out.
Yeah.
The last time I took it out was 2 or 3 weeks ago.
He's a wild child.
I have no tattoos and I've never dyed my hair, so. My daughter dyes her hair 3 or 4 times a year. And my oldest child has tattoos. Now. So now we're going to be talking about the cosine function. Well, what happens here is now cosine of 0. Well, this point here is 1, 0. So the cosine of the angle 0 is 1. And that's what this point represents. And so that's this point. pi over 2, up here, the cosine of pi over 2 is 0. So that's this point. And pi takes us half a circle. Well, the x value here is -1. So that's the cosine of 0. I mean, cosine of pi. Cosine of pi is -1. The sine of 3/2 pi, well, 3/2 pi is down here, and the cosine of this is 0. So cosine of 3 pi over 2 is 0. And then 2 pi brings us back to 1. So this is a period of cosine. Cosine has the same period of sine. Values change a little bit. The graphs look an awful lot alike. They've just been shifted. They've been shifted by pi over 2. Or is it pi over 4? Okay. I think it's pi over 2. So this chart here shows what happens from when we have 0 and then 3 pi over, then pi over 3, and then 2 pi over 2, and then 2/3 pi, pi, and 4/3 pi, and 3/2 pi. And then that's very short. Now, the reason the sine did pi over 6 and 5 pi over 6 and 7 pi over 6 is because those give you the half, 1/2, -1/2. Okay. And so that's why they're using the 1/3 angles or the 60-degree angles, 60, 120. So that's the pi over 3, 2/3 pi, 4/3 pi, 5/3 pi, because those measures, those cosine measures are 1/2 and negative. Now, the domain is a set of all real numbers. The range is from -1 to 1 inclusive. And then the cosine, as we talked, is an even function. So if I come back over here, you notice that along the y-axis, if you go in both directions, the y values will repeat as you're going along. So that shows this relationship, that it's symmetric across the y-axis. So that's indicative of a function. Yeah, and it's symmetric with respect to the y-axis. Cosine is periodic with a period of 2 pi. The x-intercepts are the odd multiples of pi over 2. So these numbers are pi over 2 plus that's 1 pi plus pi k. Want to keep pi apart. What's wrong with it? So, for the odd multiples of 2 pi, I mean pi over 2.
If the power, like x has a power 2 or the power 3, trying to remember what way that moves the graph. The stretching, right?
Oh, if we're dealing with cosine x squared, that's a different animal. We're not talking about those. Different kinds.
Sorry.
No, that's fine. So it's an odd multiple of pi over 2, or pi over 2 plus k pi. Where k is the maximum value is 1. And it occurs at the, yeah, this is where they have it wrong. That's right. So this should be the even multiples of pi. So that's not there, that's not there, that's not there. And so it's the even multiples. Even multiples. So that would be negative pi, negative 2 pi, 0, 2 pi, 4 pi, 6 pi, 8 pi. And the minimum values are at odd multiples of pi. So 1 pi, 3 pi, 5 pi, negative 1 pi, negative 3 pi, negative 5 pi. So now they want us to do the same things, but we're just jumping straight into, we're doing 3 times x and 2 times the cosine. So,
I'm gonna start with the base graph, so I'm gonna work it up.
Yeah.
Oh, yeah, well, this is the new base graph anyway, so I can-
yeah. So cosine at 0, it's 1. At 0, it's 1. At pi over 2, it's 0. And at pi, it's at negative 1. We have 1. Negative. And then 3 pi. 2. At 3 pi over 2, we're back to 0. And at 2 pi, we're back to 1. And so at negative pi over 2, again, it's going to be at 0. And at negative pi, it's going to be at negative 1. So this one kind of goes like this. And I like, okay, so I don't know if they go after the change in our x, or no, they do the 2. They attack the 2. So what happens there? So I'm multiplying each of the y values here by 2. So that means I'm going to end my smallest y value is going to be a negative 2. And my largest y value is going to be a positive 2. And so this -1 comes down here to -2. As 0 stays at 0, and the 1 bounces up to 2, 0 stays at 0, and this one bounces down to -2. 0 stays at 0, and this 1 bounces up to 2. So with the 2 here, we're changing the y values. The x values remain the same. And so go through that 0. Yeah. Not drawing the scale. My scale is constantly changing. Okay. And then the last thing we need to do is this 3. So we're going to divide each of the x values, or we're going to multiply by 1/3. So 1/3 of -1/2. I mean, of negative pi is negative pi over 3. Well, yeah, I'm multiplying by 1/3. So that's the same as dividing by 3. So this y value got moved to there. Oh, okay. So this comes back to 1/3. So this point up moves back to 1/3. The y, now the y value remains the same, and I'm changing my x back. Right. 1/3 of 1/2, or 1/2, -1/2 times 1/3 is a negative pi over 6. So this point got moved to there. And 0 stays 0, so that point didn't move. That's the only point that's not going to move. And then 1/3 of pi over 2 is pi over 6. So this point got moved over to here. And pi, we're going to take 1/3 of pi. Isn't that over here? Pi over 3.
Wouldn't that be on the right side?
That's on this side of 2, right? Just a second. Yeah, no, it's on this. It's over here. Pi over 2. Pi over 3. Pi over 3, sorry. And that's this point gets moved over there, so this gets moved over to here.
Oh.
So yeah, I think this is supposed to be over here. This is closer over here. So yeah, 1/3 and 1/6. So that got moved over here. Not and then 3/2 becomes 3/6 pi, which is pi over 2. So this one came all the way down to here.
Oh my gosh.
Yeah, because we're taking a third of the distance. And compressing it this way by 1/3. So I'm gonna take a third of 2 pi, which is 2/3 pi, which is here. And so this point happens over here. Over here. So now thinking electronics, this is the frequency got increased. Oh, that's supposed to be a little bit further this way. So, yeah. So if I had graph paper that had better grid margins, this would look better.
Why is pi over 2 after pi over 2?
Because the larger the denominator, if the numerator is the same, the larger the denominator. So a half a pi is more of a pi than a third. A third versus a half.
So it's split, like on the negative side, you have negative pi over 6, negative pi over 2.
Because you're going the opposite direction.
Oh,
So this is more, this would be a larger negative than this would be.
That doesn't look right. Yeah, negative pi over 2 and negative pi over 3 is switch. On the negative
Oh,
side.
yeah.
Sorry,
Yeah,
I'm confused.
yeah. This should be over to here. And this because this was pi over 2, and this should have been negative pi over 3. Yeah. Okay. I had kind of screwed up there. Sorry. Yeah, and the negative numbers, it gets a little confusing. I tend to stay in the positive. Their pictures are prettier and they're not on top of each other like mine are. So,
Okay, so last time in your class, you quoted Jurassic Park. You said, let's go faster.
said what?
You said, let's go faster. Yeah, like Jeff Goldblum when they're being chased by the T-Rex.
I remember that.
And that stayed in my head. I was like, where did that come from? Why did he say that? I know it's from a movie. And then it hit me at work and I was like, let's go faster. Let's go faster.
Well, I wasn't necessarily quoting them, but yeah, it comes out that way. So what they did here, they multiplied the y values by 2 to get this graph. And then they redraw this graph, I think, yeah, over here. And then they're going to multiply each x value by 1/3. So this negative pi became negative 1/3 pi, where the y value remained the same. This negative 1/2 pi became a negative 1/6 pi, and the y value stayed the same. 0 stayed 0. And the pi over 2 became pi over 6. And then pi became pi over 3. And then 3 pi over 2 became 1/2 pi because it became 3 pi over 6, which is 1/2 pi. And then 2 pi became 2/3 pi. The y value remained the same. And then 5/2 became 5/6. The y value remained 0. So this scale is a little spread out further than that one. So if this scale matched that scale, it would be compressed in. So where one goes like this, the other one goes like this. So the frequency increased. If you think of it in sound waves or in electronics, the frequency is increased. And that's omega. Well, it's related to frequency. And the range, all we did was change the range. We didn't change the domain. And the range, simply by multiplying by 2, changed our range from -1 to 2 to 1 to -2. And then they put them into calculator. So this is the cosine in blue, and the 2 cosine of 3x is the red. That's what my graph should have looked like. Okay. This is a shift in the period. So I'm shifting it 2 pi to the right. Because if I'm subtracting from x, that's going to be a shift to the right. So my 0, 0, the red is the cosine. So 0, 0 got shifted over to here. And so this point got shifted over to there. So this whole graph just got shifted half a pi units to the right.
Yes, they're subtracting to the right and adding to the left.
If you're changing your x values, a shift in the horizontal, a shift to the right is minus a number. A shift to the left is adding. So I look to see what happens to my 0, 0. What makes this in here 0? So that's pi over 2. So now, so that moves my y-axis over to here. So this is cosine, which is a cosine of x minus 2 pi, which is a sine of x. So sine and cosine are just a shift by pi over 2. You get the same values, it's just they're shifted. What angle gives them those values is shifted by a half a pi. That's all they're talking about. And so that's a phase, yeah, that's a phase shift. The phase shift is a horizontal shift for sine and cosine in all the trig functions. Okay. So here we have a theorem. If omega is greater than 0, the amplitude and period, the amplitude and period, if you have a sine omega x and a cosine of omega x, the amplitude is the absolute value of A. So if, like on one we had a -2 sine, the amplitude is 2.
Yeah.
So the amplitude tells us how high and how low we're going to go. Now we might shift that because we're adding and subtracting afterwards, but in the period, which we usually represent with the letter T for some odd reason, is 2 pi over omega. Because dividing by omega is what happens with our x value. That shifts our x values either towards the y-axis or away from the y-axis. If omega is a fraction less than 1, then it's pulling it away from the y-axis. If omega is greater than 1, it's pulling it towards the y-axis, like on the 2 examples we have. So now this helps us. This helps us because we know our period is 2 pi. So with sine goes like this. So, and this is from 0 to 2 pi. And if I know the new period now, then I can just shift it this way. I just compress it this way. And if omega is greater than 1, and if omega is less than 1, then I'm pulling it up, and then I'm just stretching it out. So it's like I take a slinky and I pull it apart, or I push it back in. So the amplitude and period, or what is that? 3, 5, 5 sine 3x. So the amplitude is what?
Oh, it's 5.
5. And the period is what? The period
It's 2 pi over omega.
pi over omega. And what's omega? No, 3. Leave the x alone.
Sorry,
So 2 pi, 2/3 pi. That's all we were asking. So A is 5. Omega is 3. Amplitude is the absolute value of A. And the period is 2 pi over omega. We'll graph this using key points. Right, so we will assign the key points for sine. 0, 0. Over 2, 1. Pi, 0. 3 pi over 2, -1. What's the next one? Two pi, right? Back to 0. Well, the amplitude, I'm multiplying each of the y values by 5. So that becomes 0, 0. This becomes pi over 2, 5. And this stays pi 0. And this becomes 3 pi over 2 negative 5. And this stays 2 pi 0 because 5 times 0 is 0. So now I'm going to divide each of the angles by 3 or multiply by 1/3. So 1/3 of 0, 0, so 0, 0 stays, is left alone. And so this becomes pi over 6, 5. This becomes, bless you, pi over 3, 0. Because now all I'm doing is changing my x values now. I changed my y values, now I'm changing my x values. This is going to be pi over 2, negative 5. And this will be
Oh, sir.
2/3 pi.
I'm confusing those numbers when you have those numbers on top. You have 2 sine, that's 2x right there. Why are you using those? You see, it says up right there, it says graph plus 2 sine times 2x.
So where did I get 5? Oh, that was the other problem.
Yes, sir.
Okay.
Sorry. We can keep those numbers though, sir, and still use them.
Because they want us to graph it. So to graph it, okay, so my initial values remain the same, but now my amplitude is 2, and my period is 2 pi over 2, which is pi.
Well, that's good, right? 'Cause that's easy.
So I'm multiplying each one by a half to change my period, but to change my y values, I'm just multiplying by 2. So I'm multiplying each of the y values by 2. So this is 0, 0. This is pi over 2, 2. This is pi 0. And this is 3 pi halves negative 2, because 2 times negative 1. And then here I have 2 pi 0, because 2 times 0 is 0. Now this was doing 1/2 times 2 pi. So that's what changed it to pi halves. So what did I do to change it? Well, I multiplied by 1/2. So I multiplied each of the x values by 1/2. So 0 times 0 is still 0. So 0, 0 stays 0, 0. The only point that hasn't changed. And now I multiply 1/2 by 1/2 pi by 1/2, which gives me pi over 4 and the 2. And then this is just pi over 2, 0. And this is 3/4 pi negative 2. And this is pi 0. So to graph this, I don't even need to look at the changes. I'm just looking at the changes of my key points. And 0, 0, it stayed 0, 0. And then the next one is that well, let me see. So this is pi, because that's all I have here. So 1/2 of pi, and then pi over 4, and then pi over 2, and then 3 pi over 4. So, and this goes to 1, 2, and 1, -2. So 0, 0, and then pi over 4 is at 2. Half a pi is at 0. 3/4 of pi is at -2, and then pi is at 4 again. And so then we have this. Isn't that easier than doing like that, the different graphs, doing the transformation?
Not like.
This is where we're doing, we're just gonna do the transformations on the key points. And then sketch the graph.
Yeah, my sister's taking algebra and she was like saying she needs a graphing calculator to do the picture of the graph. But every time I've been with you and we do it, we get the points and then we make the graphs. That's like where I was like, you don't need a graphing calculator. You just find the points and draw the graph yourself.
I don't like using graphic calculators. Because then you don't understand what's happening. You can see what happens, but you're not understanding what happens. So I'm gonna erase this. I can't read what they wrote, and we're actually over time.
Wow.
So yeah, yeah, so they talk about what the period is and what the amplitude is, and then they change, goes from -2 to +2, and so they look at, so they divide the interval into 1/4. So from 0 to pi, they're going to divide it into 1/4 seconds. And that's what they're talking about here. And they're doing the same thing, but they're looking at it a little different. And so I just start with this. Oh, okay. I get to this point the same way, and but slightly different ways. These are the points of the graph, and that's the same points. By looking at the period and then dividing it into 4 sections, because that's what happens. So you have 4 sections within the 2 pi, and so that period got knocked down to pi, and so you divide that into 4 sections, and then the 2 from there. Okay, bye. We be done. Yeah, I knew we were getting close to the end of the time, but I just get so involved. Okay.
We haven't finished, we had already started it.
I still haven't received my access code for my.
Send me an email, and yeah, that's constantly bugging me about it.
Have you got YouTube to go up, sir?
Well, I keep trying to redo the YouTube channels, and I just haven't been able to sit down and do that.
Okay.
Okay.